Hello, everyone. This is Dr. Lennon, and I just want to go over a handful of the homework problems, some of the more difficult ones some other people have asked me about. The first two are order of operations, so I think everyone should be able to have a handle on that. The main thing is to remember that division and multiplication are not different operations. You just do them as they appear from left to right. So, for instance, in the denominator of number 1 over here, you're not going to multiply 8 times 4 before you divide 72 by 8. So you do 72 divided by 8, which is 9, and then multiply by 4, which should come out to 36. So the denominator underneath the radical should simplify to 36 in this problem. I don't know, why don't we just go ahead and do that? So let's include that as 1. So number 1b, let's say. So we've got the square root of 15 squared minus 12 minus 3, excuse me, squared divided by 72 divided by 8 times 4. So, we're going to simplify inside the parentheses first. So we have 15 squared minus 12 minus 3 is going to be 9, so we have 9 squared, and then we have 72 divided by 8 times 4, and then we're going to simplify the two exponents on the top, so that's going to be 225 minus 81, and on the bottom, so we treat the top and the bottom when we have a complex fraction like this as if they're in parentheses. We do this from left to right. So 72 divided by 8 is 9. So we're left with 9 times 4. And we have the square root of 225 minus 81. Should be 144. So we have 144 over 9 times 4, which is 36. So let's see. How does that simplify? So 144 is 12 times 12, and 36 is 6 times 6. So this is just the square root of 4. And the square root of 4 is 2. So that problem simplifies all the way down to 2. For number 2, please remember that your final answer should only contain positive exponents. So remember the main rules we're using here for number 2. We have our laws of exponents. And sometimes I number these differently, so let's not forget. 1, we have a to the m times a to the n. If they have the same base and you multiply them, then you add the exponents. So this is m plus n to a to the m over a to the n is a to the m minus n. So probably, let's see, if you have a to the m in parentheses, then raised to the n, this is where you would actually multiply them. So it'll become a to the m times n. We also have where you have multiple factors. If you have an a and a b both being raised to the n, that simplifies to a to the n times b to the n. So those are being multiplied. Then, we have some oddities like a to the 0 equals 1, provided a is not equal to 0. We have a to the negative n is the same thing as 1 over a to the n. So those are the main rules we're working with here to simplify all these things. So let's just pick a few random selections. So let's say number 2. So let me move this over a bit. Yourself a little extra room. Why don't we start with e, let's say. So there you would have x to the 4th over 3y quantity squared. So really we're making use of this rule ab to the n is a to the n, b to the n. Each factor inside needs to be squared. So this is going to be x to the 4th squared on top, and then on the bottom 3 squared and y squared. So you square all 3 components. The top we're going to apply the third rule. If you have parentheses m raised to the n like that, then you multiply them. So 4 times 2 makes 8, so the top is x to the 8th. 3 squared we know is 9, so that's 9y squared. So that would be how you would do E. One like J is actually kind of simple. X to the negative 2, y to the negative 3. Basically, this is a one-step problem because if the exponent is negative in one part of the fraction, it will be positive in the other part of the fraction. So y to the negative third is the same thing as y to the positive third on top, and x to the negative second is the same as x to the positive second on bottom. Why don't we do one more? Why don't we go ahead and do, let's have a look at, say, L. So we can do L over here below. So it's kind of box that off. L just looks intimidating, so I figured we'll give it a go. Maybe it's not. So 5x squared over y to the third, that whole thing raised to the negative second. There's kind of two ways to do this. You could apply the negative and just flip the fraction, or you could apply the negative 2 to each thing. I think it's a little bit easier if you take the negative and you just flip it over. So the negative is going to put the 5x squared in the denominator and the y to the third in the numerator, because you need to apply the negative to each factor, so it would make all of their exponents negative. So to write them with positive exponents, we would go ahead and just flip them. So basically this now becomes y to the third over 5x squared, and instead of the negative 2, now it's the positive 2. And then the rest of it works just like the problem we did before. I think it was kind of part G. You just apply the squaring to each factor on the inside. So you have y to the third quantity squared over 5 squared, and then you have x squared squared. So multiply your exponents. So top 3 times 2 makes 6. 5 squared is 25. And x squared squared, 2 times 2 is 4. So those are those laws of exponents. Now we want to work on some of these radicals. Simplify them. Some that are pretty simple we're not going to really work on. So let's do number 3. Let's look at G. Well, these go vertically. I'm used to going left to right and then vertically, so I'm kind of doing them out of order. So let's not start with G in that case. Let's look at, I don't know, B, the square root of negative 25. When you take the square root of a negative, this is not real. You'll get a imaginary number. And I don't think we work with those too much. So for some of these, they're just clear inverse operations, E and F. Those are just very simple. C, although we have a cube root of a negative, remember, you can have cube roots of negative numbers and they come out negative, because a negative power or a negative number raised to an odd power will still be negative. So this would be the same thing as, let's see, we could just pull the negative out when it's a cube root like this, because like I said, that is an odd radical. And then we know that, so cubes will undo third powers. So 27 is 3 times 3 times 3, 9 times 3. So that's 3 to the third power. So the cube power will cancel with the cube root, and it will just leave us with negative 3. Another way to think about it as well is also we could check, and if we do negative 3 to the third power, we should get what's underneath the original cube root, which we do, right? Because this is going to come out to negative 27. So it checks out. Okay, what about one like, let's look at G and I. So for one like G, the square root of 9 over 100, Radicals behave well with multiplication and division. So that means that I can just write this as the square root of 9 over the square root of 100, which comes out to 3 over 10. And that's a fraction in simplest form. I wanted to look at because it is the square root of 45. So although 45 isn't a perfect square, we can write it as a product of something that is, right? 45 can also be written as 9 times 5. And the reason we want to write it like that's the way we can break up the radical with division, we can also do with multiplication. So this is the square root of 9 times the square root of 5. 5 is a prime number, so that's as simplified as that part's going to get. But we know 9 is 3 squared, so the square root of 9 is 3. So this would simplify to 3 square root 5, and that would be it. Okay, number 4. We have basically the fundamental way to transform from, let's say, radicals to exponents. And it goes either way. So you can change any radical into an exponent, or you can change any exponent into a radical if it's a fraction. So basically, if you have a to the m divided by n, this can either be written, so the bottom of the number is like the root. So n is the root, and m is the power. So you could write it like that, or equivalently, you could also write it as the nth root of a to the mth power. It all kind of depends. So for some of these, you're just writing them as the radical and then simplifying. So why don't we look at I don't know. Let's say something like c. So if this is c, we have negative 32 to the negative 4/5. So since the root is 5, we know it's going to work well. But the exponent's actually only being applied to 32. It's not being applied to the negative. So I'm going to go ahead and use this last thing. So I'm going to say, okay, this is the negative, and then I'm taking the 5th root of 32 to the 4th power. So that can be simplified because 32 is, let's see, 32. Oh, the 5th root, yeah. 32 is 2 to the 5th power. So the 5th root of 32 will just be the number 2. So we have negative, and then the 5th root of 32 comes out to 2, and this is the 4th. If you don't have access to like a calculator or something like that, a good website I like to use for like a scientific calculator is desmos.com. So you can do the graphing calculator, but there's also like a scientific calculator if you click Math Tools. So the scientific calculator, say we wanted to do that 5th root of 32, we were having trouble doing it, we could just type it there. So we could type the 5 as the root and the 32 is the number, and then it tells you the answer is 2. So if you're struggling to identify the powers, you can use this desmos.com and choose the scientific calculator. Okay, so that was C. This should actually probably be in the laws of exponents one. We don't really need to use radicals there. Okay, let's look at 2 more. So I want to look at D, and then I also want to look at that last one. I guess we'll call it F. 121 to the negative 1/2 over 100 to the 1/2. So remember, the negative exponent means we can put it on the bottom, and it'll now be a positive. So if we move it to the bottom, there will be nothing left on top, so we'll write a 1 there. And then it'll be 121 to the 1/2 and 100 to the 1/2. But we know 1/2 power just means square root. So if the root is 2, that's square root. So this is the square root of 121 times the square root of 100. We know both of those square roots because 121 is 11 times 11. 100 is 10 times 10. So this is just 1 over 11 times 10, or 1 over 110. Okay, and then I said I also wanted to do f. So this one actually would be more of a rules of exponents, at least the way I'm going to do it. Because you have the same base there, 5, and you have 2 exponents. So the rules of exponents, this was the very first rule. It said we can say this is 5 to the 1/2 plus 3/2 all in one exponent. Well, 1/2 plus 3/2 makes 2. 0.5 plus 1.5 is 2. So this is 5 to the second power, and 5 squared just comes out to 25. Okay, let's see what kind of laws of exponents problems. Just a couple here. Again, the only difference here is they're using letters instead of numbers. So they're not going to work any different. The only difference is where we get something to simplify, like 5 squared, if you ended up with x squared, that would be your answer. You're not going to be able to simplify that to a number. So let's just look at number 5. Let's do the one in the middle. Let's do b. So we have 4y to the minus 1/2 over y to the minus 2/5. Okay, this is rule number 2. The y part is the same, so what you can do is you can just subtract the exponents. So we have the 4, and then we have the y, and we have negative 1/2 minus the bottom exponent of the y, which is negative 2/5. So now our expression is basically 4y to the minus 1/2, and minus a negative is plus a positive, so that's plus 2/5. So then you need to get a common denominator. The easiest one would be tenths. So negative 1/2 is the same as 5 over 10, so this would be 4y to the negative 5 over 10 plus 2/5 is 4 over 10. So negative 5 over 10 plus 4 over 10 is negative 1 over 10. So we have 4y to the minus 1 over 10. And that is the same as if they want positive exponents, the y would have to go to the bottom. So this would be y to the 1 over 10. And it doesn't say anything about using radicals, but if we wanted to write it in radical notation, we could write it as 4, and then this would be the same as the 10th root of y. So probably either of the last two expressions are satisfactory. So this last one, number 6, the only thing it looks like is going on is we have this formula. So let's write that formula out. It says f, that's a cursive s, is equal to 24, and then it looks like the square root of d. So to find the speed of the vehicle before the brakes were applied, s equals 24 square root of d. So I'm guessing s is speed and d is the length of the skid marks, the distance. So basically you're just using that 175 number here and then simplifying that problem. So since it doesn't mention it exactly, we'll say s is equal to speed and d is equal to length of skid marks. So with that, you should be able to finish that problem. It's not a very difficult problem. There's only one number mentioned. Again, it wants you to round your answer to the nearest tenth, so you may want to use that Desmos calculator to figure that out here. But anyway, hopefully I've answered your questions for this homework. Good luck and get that finished, and I will see everyone next class.